Good evening, folks, and welcome to the Advent of Code C++ live stream. My name is Craig, and tonight, as we do every night during Advent of Code, we're going to be working through the new puzzle drop in C++, seeing how far we can get. So far, we haven't had any real stumpers, but we're getting into that section of the puzzles. Each year, the puzzles tend to get a bit harder as time goes on. So you never know. We may find that tonight we hit a real stumper and might have to step away and think about it more. But we'll see what we can do. So far, we've been doing pretty well. So last night, for day 16's puzzles, we wrote this binary parser for this message format to get our message from the elves. And it wasn't anything algorithmically too difficult, but it was just a matter of, following the instructions very closely, going bit by bit, parsing out the information that we need. And it's, it's not all that dissimilar from, like some real binary parsers that you use for some serialization formats like protocol buffers or probably some other similar ones like maybe Apache Thrift and that kind of stuff. So tonight, who knows what we'll do tonight, but we've got the skeleton for tonight's program already set up. We've got a very basic main function here that doesn't actually do anything yet. It just returns 0. We have already included the check library and the IO library that I've pre-written to use in these puzzle solutions, and we've set up a build file for the Bazel build system that we're using that just tells it how to build this program. So we can go ahead, tell Bazel to build and run it here, and it does nothing. It just returns to the environment. Since we've got a little bit of time, a couple of minutes before tonight's puzzle drops, I'll just give a quick look at those libraries that we use pretty much every night that I pre-wrote. For check, there's just a couple of macros here that expand out to these basically do the same thing that assert does, except that they do it no matter what configuration you build in, because the normal assert macro from the C standard library requires the ndebug, not debug symbol, to be defined. No, the debug. No, it require if ndebug is defined for not debug, then it doesn't activate. I know there's all kinds of like double negatives. So as you can tell, that makes it a little confusing to use assert sometimes because whether it's actually active depends on your build settings. So these checks are just active all the time, but they basically do the same thing that assert does. For IO here, we've got functions that read input from files, because we pretty much always get our puzzle input as files. We can either read the whole file into a string, read the lines of the file into strings, or read comma delimited substrings from a file. And then there's some stuff where we can, parse integers from those strings that we parse, or split up segments of the parsed input by empty strings, and all the implementations are there. So you can always look at the full code for this stuff. I know I'm jumping around here pretty quickly, but you can always find the code for this in my GitHub repository for Advent of Code. You'll find a link to that if you're watching on Twitch. It's in my channel profile. If you're watching on YouTube, there's a link right down there in the video description. So we have just about 35 seconds until tonight's puzzles unlock. Day 17. We're getting close to the home stretch here. We have finally emerged from the cave in our little submarine in our search for the lost sleigh keys. We've gotten our message from the elves last night. So we'll soon see what the next step on our undersea journey is. Few more seconds now. Okay, trick shot. Hi, the else message says. Continue searching through keys. There's a large ocean trench. Better send a probe to investigate. Probe launch range summary, you can fire the probe with any integer velocity in the x, forward, and y, upward or downward if negative directives. For example, initial xy velocity like 0, 10 would fire the probe straight up. Initial velocity 10, -1 would fire the probe at a slight downward angle. Probe's xy position starts at 0, 0. They'll follow some trajectory by moving in steps. Each step, these changes occur in the following order. Probe's x position increases by x, y position increases by y. Due to drag, x velocity changes by 1 towards the value 0. That is, it increases by 1 if it's greater than 0, decreases by 1 if less than 0, or does not change if already 1. Due to gravity, y velocity decreases by 1. Okay. In order for the probe to successfully make it in the trench, the probe must be on some trajectory that causes it to be within the target area after any step. Okay, so we've got this target area as our puzzle input, a range of x's and y's. This target area means you find the initial xy velocity value such that after any step, the probe's x position is at least 20 and at most 30, and the probe's y position is at least minus 10 and at most minus 5. Okay. Telling us about the coordinate system, x increases to the right, y increases upward, and we've got this target area. And we see the trajectory in each of the steps here. It appears to pass through the target area, but is never within it after any step. Okay. How high can you make the probe go while still reaching the target area? Interesting. Find the initial velocity that causes the probe to reach the highest y position and still eventually be within the target area after any step. What is the highest y position it reaches on this trajectory? Okay. Fun stuff. Let's save our link here. It's day17.txt. So let's look at how that input looks. Okay. So we've got our target x and y there. Now, we do have a 2D geometry library that may be able to help us with this. So I'm actually going to just encode the input directly into the program rather than parsing it, just for the sake of speed. So I'm going to say const expert in 64T target x min is 57. Okay, target x max is 116. And then similarly, we'll put the y's in here as well. And we will have done manual human parsing of these. So we don't need to do anything more with the input. So that's minus 198 and minus 148. So then let's have a class called probe, and so no matter what, I'm seeing this here. the higher the initial y velocity, the higher the probe's peak is going to be. And so we can do a search through y velocities, just like trying to get, like a higher and higher initial y velocity. And then for a given y velocity, we need to calculate, like, if an x velocity would be valid. Like, if there's any valid x velocity that would put it inside the target area. So, for the probe, its position, well, we're going to use my 2D grid geometry library because it already has some useful stuff for us. So we'll include grid 2, and we're going to just use that whole namespace so I don't have to type out whole lines and everything. So point is going to be, there's going to be a point position that is initially at the origin, which is actually just the default value for that. And there's going to be a vec velocity and then well, so I actually, now that I'm beginning to think about this, the way to solve if there's any valid x in range is to, I think, find the x. Maybe we don't even need to use my geometry library quite yet. I'm just thinking about the constraints on this problem. So for any given y, you can calculate what are the number of steps that it's possible for because if you just graph like y over time, it's going to be a parabola because its second derivative is going to be -1. And then, so we should be able to solve for how many steps are actually in that range between -198 and -148 for a given y. And then we can try and solve for x in such a way, we could solve for like possible x's and see if they're integers. So I'm actually going to try and apply some math here and maybe not even use the grid library quite yet. So for now, I'm just going to take that away. But we'll say so y steps for initial dy. For a given initial y velocity, this will tell us how many steps it will take to be within the target y range on either end. So we'll have that initial dy, and let's see here. Just looking up the if I remember, it's we've got constant acceleration. Yeah, so it's 1/2 t squared. I knew. Yeah. Okay. Um, so basically, we're going to have an equation where y is equal to, and I'm just going to like put this in a comment. So y equals dy times t plus half of -1. So we'll just say minus 0.5 times t squared. And we can find, we can basically, I mean, we can use the quadratic equation to solve this. So we'll do this is more of a physics problem than a programming problem, but we'll get there. The A, B, and C coefficients. So so there's it's the quadratic equation. Man, taking me back to high school algebra is minus b plus or minus the square root of b squared minus 4ac over 2a. So that plus or minus term we're going to pre-calculate as square root of b squared, which can just be b times b, minus 4 times a times c. And you know what? I'm going to pass all of these as doubles as well, because at least some of them are not going to be strictly integers in the input here. So we'll, and actually I'm going to make this a vector of doubles. It can be up to, it can have 0, 1, or 2 roots. So yeah, and that would come out to a nan. So we'll just say double under root is that if under root less than 0, return an empty vector. There's no solutions. If under root is exactly 0, then return minus b over 2a. Otherwise, our two solutions are now we can actually calculate the square root of that term that's under the root, and the two solutions are going to be minus b plus root over 2a and minus b minus root under 2 over 2a. Okay. So we've got our little quadratic formula solver, and so now we've got this answer that gives us y. So I mean, we're always starting a parabola, but I think in this case, so the parabola is starting at 0. It should always have one solution for a given initial y velocity when it hits the top and bottom, because the initial position is at 0, 0, and we're always aiming for a y position that's lower than that. So we'll say we'll do quadratic solve here. And for A, B, and C, and C should be double as well, we're going to convert all these back to integers and find if, there's an actual discrete number of steps that we can take. But here, the way that this will actually work is, it'll be, like k target y max equals dy times t, that whole thing. So what we'll actually have is 0 is A is 0.5 minus 0.5 rather. B is dy, and C is minus k target y max. So for this, we'll do, and then B, let's see, B is dy as we said, and C is minus k target y max, and that should have only one element. And then we can do the same thing for the minimum value, which we'll actually get to further because it's further down in space. So we'll say step min double a target x max. Okay. For now, I'm just going to, do void here. Well, no, we can do this. We'll go ahead and do this. So, we're going to want, for the y max, we're going to want the ceiling function on that, because we want the number of steps that is at least the actual, like continuous step size that we can calculate and double. And then for the minimum one, we can do the other one. So we'll just do, we want the floor, because again, we want the largest that's not greater than the other bound. Okay. So at this point, I think it's probably a good idea just to do a little safety checking with the sample input. So I'm going to comment out what we have here for our actual puzzle input, and I'm going to replace it with the test input for the test. So the the demo input they gave us basically was 20 to 30 and minus 10 to minus 5. So so one example they give us that works is 6-3. So let's just see like what step range it gives us for 6-3. So so 3 would be the initial dy there. And we'll say just, you know, see what that gives us here. Okay. Oh, well, I don't actually think we're using grid 2 right now, though, so I'm going to actually get rid of that include for the moment. Comment that stuff out. Okay. We got to this point. So we somehow got multiple solutions there. Let's see, did we get 1 or did we get 0? Excuse me, did we get 2 or did we get 0 is the question. Let's find out. We got 0. Because the under root term then was negative. Oh, yeah, because that should be minus 0.5, shouldn't it? Let's try again. Still wrong. Okay. Shouldn't have taken out that debugging statement quite so soon. Watch it be 2 now. Okay. Let's just print out what it thinks they are. And this will maybe give me some insight into what I'm doing wrong here. Oh, some are negative. Yeah, because if you go back in time, of course, but we can only go forward in time is the lesson here. So, yeah. So we'll just write another helper function. Positive vibes only. I mean, really non-negative. I guess 0 would technically be okay, although we wouldn't really reach it, but just basically 4 double value. Well, actually, yeah, let's start it as -1. In that case, we should check fail, because that means that we found more than one positive. Otherwise, we return value. And actually, yeah. No. Well, we'll replace that there because we'll go ahead and be thorough in our checking here. Check fail if we didn't find anything positive, then we return one positive that we had. So now we'll say step max double is positive vibes only applied to quadratic solve. And that's a double. And oh, that shouldn't be X max, should it? That should be Y min. It's another good bug that I caught just reading over this function again. Now this should still... Okay. Let's run that one more time. Gives no input somehow? No output, rather? Come on. Huh. We have that C out there. We have that. Don't know why it would stop without doing anything. Doesn't get that far. Okay, we get in there. Do we get this far? No, we don't get that far. For value and values, if value is greater than 0, if position has already been overwritten, we fail. Otherwise, oh, you know what? Check fail. I think it's in how I've written check fail that it doesn't play nicely on a single line like that. So this should that's my fault in writing the library poorly. So now I'm looking at the number of steps of the example. It's 1, 2, 3, 4, 5, 6, 7, 8. No. Okay, now that seems like it's... 2, 3, 4, 5, 6, 7, 8, 9. It should actually be 9. Should be the number. So It looks like some kind of an off by 1, but I'm thinking here. I'm realizing now that, like, we're applying acceleration continuously, like we're doing it like the calculus way, but the drag is actually, gravity is actually doing this in discrete steps. So this whole thing where I saw something that looked like a physics problem and tried to start solving it in a physics type of way, may have been a bit of a garden path because, like, the acceleration is really not continuous. Um, it is a step function, so instead of man, well, which makes me think maybe we go back to brute forcing it. Okay. So realizing that I've done all this wrong, let's okay. Let's rethink. Let's regroup. Think about what the correct way to approach this is. So honestly, we could just search at brute force, and there is a way to do this mathematically, and maybe that'll jump out to us. But at this point, I am now wanting to do this brute force, so I will get rid of, or at least temporarily comment out. You never know. The next step might want us to do it the quote unquote right way, but for this, we'll just say we'll just so we'll have min step and max step, and then we'll just simulate the steps, counting only y right now. So number of steps will start from 0. Well, actually, we'll just say y position is initially 0. And while y position is greater than or equal to the minimum y position of the target, we will say if y position is also within the range, so we'll say if y position is less than or equal to the maximum target y position, then this is a valid step. So let's say if min step, well, actually, we'll make these -1 initially, like an invalid number of steps. So say if min step is -1, then we will replace min step with the current number of steps. So we'll just say step is initial min step equals 0, and then Max step, we'll just unconditionally set to that as long as it's in range. Then dy will decrement dy after, yeah, and then we will increment the step count, and then we can actually, I'm going to make this an optional so that we will only return a value if there's anything that makes sense. So just say if these are both non-negative, if we've actually successfully found a step, then we will return in step to max step. I think we may need to double bracket that. I'm not sure if that will actually, yeah, that'll actually work. Otherwise, we will return null opt. You can't even get to y there. Okay. So steps for initial y. Now we will do the similar test that we were trying to do before, and we will say check test steps dot has value, and print out the first and second there. Okay. We have clearly we haven't actually changed ypos at all, have we? So then y plus equals dy there. That's so, you know, on step 0, it will apply that, and yeah. So that should do it now. Forgot to actually update the position there. Okay, now that's saying 0 to 9, but oh, min step should equal step, not 0, of course. There we go. 9 to 9. Thank you. Okay, finally we got somewhere that didn't look completely wrong. Okay, so now then the other thing we need to do is within that range we need to find if there is some dx that would put us in the proper range for that. So we can say, so we can find if a particular dy is valid at all. And actually, while we're doing this, since ultimately it's wanting us to give the highest y position it reaches on its trajectory, since we're simulating the y trajectory in this, we might as well do that as well. So we'll just say we'll have a struct called yinfo here, and we'll say and we'll have another field called peak, which will be its peak y value. So we'll have this return this yinfo struct. And we can keep track of the min step and the max step in there. And we'll say info.peak before we update the y equals the max of the existing peak and that y position. So just return info in that case and still return null opt if not. So can still do min step and max step here. But now I also want to see what the peak is. So let's do test steps and to peak. See what that looks like. Okay. It says the peak is up 6 and 1, 2, 3, 4, 5, 6. What do you know? That actually is correct with the inputs that we have so far. Yeah, I'm sorry I'm going a little slow tonight. I could definitely tell that we're not going to be like lighting up the leaderboards tonight, especially because of that garden path diversion, trying to solve this like an actual physics problem instead of something with discrete time. But, you know, we're getting there. So bear with me. So now we have a range of steps for a given dy that you know, gives us some possible x. So we now need to, well, yeah, we now need to figure out, like, if there's any x value that will get us there within the allotted time. So I'm actually thinking here that, like, after a certain number of steps, so, you know, we have, you know, initial x velocity, and then it's x minus 1, x minus 2, and so on until we get down to 0. I'm thinking, like, sum of consecutive integers might work here. Yeah, just did I somehow find? Yeah, searching for. Yeah. So that is the sum of the first and last number times the number of numbers over 2. Okay. So I think well, I'm just going to write out notes to myself in comments. So like, well, you can write it in code and then we can try and invert it and see if that, you know, makes sense. So we can say, you know, x after steps in 64t d our initial velocity dx and in 64t number of steps. So if so I'm thinking, you know, one step is just final dx is going to be dx minus step clamped to 0. Sorry, I'm just thinking here. Well, let's just say if step is greater than or equal to dx, then we just need the sum of the numbers from 0 to x. So or 1 to x, really, I guess. But yeah, so it would be so turn dx plus 1 times dx divided by 2. Otherwise, we do return dx plus dx minus step plus 1. So I'm trying to think here, like, after, if we just do one step, it would only be dx, and this would be dx itself. And I'm sorry, I'm sorry I'm a little slow with this math, but just try and bear with me here. So okay, so I'm just satisfying myself that this is correct. So if step were to be 1 here, then we'd have 2dx times 2 over 2. No, that's not right. So times step, maybe. Oh, man. I'm so rusty on my math skills. I apologize. Okay, so if step is 1, then that is 2dx times 1 over 2, just dx. That's correct. So if step is 2, that gives us dx plus dx minus 1 times 2 over 2. So yeah, I think this is correct now. But we can give it a little test here. So let's say with that initial thing, we'll again comment some of this out. This is a very messy explorative process that I'm going through tonight, but just to figure out this, you know, with that same 6-3 example, you know, imagining that our initial x velocity is 6, let's just go through like 1 to 10 steps and see what it gives us. So let's simulate this for 10 steps and just satisfy myself that it turns out correctly. And that's with initial dx of 6, and that step. And see if it looks like the trajectories that we get in the example. Okay, so 0, 0, then that's 1, 2, 3, 4, 5, 6. Okay, and then it's, you know, 5 is the delta, and 4 is the next delta, and 3 is the next delta, and 2, and then it gets stuck at 21. So that does look to be correct. So to figure out if there is some, we now need to figure out if there is some velocity that, given those steps, will put us in the right range for y. So if we have a known value for step, then maybe we can back we can algebra this out back to get dx. I don't know. This is where we might actually get back to the quadratic formula. So I'm just going to think here. So we'll just say maybe we just search it. um, so let's actually start thinking about our search algorithm now. So the initial dy, the very lowest the initial dy can be would be k target y min, because after one step that's going to be at the minimum possible y. Any lower dy, it's going to immediately after one step sink below the target area, and we can't get anything out of it. So that will be the absolute minimum bound. So we'll just say for k target y min, the maximum positive y, well, that's actually I don't know about what to do about that condition quite yet. We can increment the candidate dy. So we'll say equal, so step range would be steps for initial dy. We've got our candidate dy there. And if step range doesn't have a value, then I guess continue, but we're going to need some kind of termination condition for this loop. So I still need to think about what that is. But, okay, saying that we have a step range, that range is inclusive, but then we need to try and find if there is any dx that will put us into that range. So we'll say, I get a feeling that kind of the tricky thing about this is knowing when to stop these searches. But we'll say, start with candidate dx of 0. I guess the highest that candidate dx could be would be the maximum target x. And we could go less than or equal there, but if after one step it completely overshoots, then we then there's nothing to be done. So, and we could actually, I'm sure, make that condition much tighter, but for now I'm just trying to figure out brute force here, and we can come back and make these conditions tighter. But we'll check those out. The possible steps in the range. Or honestly, I feel like we should invert these because that range is going to be considerably smaller than the range of possible delta x's. But if there'll be x after steps with candidate dx and that number of steps. If that x position is greater than or equal to k target xmin and it's less than or equal to k the target x max, then we found an x that works, and we will say step range, and we will a bool found here. We can immediately break out of this loop. And if found, we can also break out of this loop. And then if found, we'll update, we'll say highest peak is 0 there. If found, we will update that as the maximum of that step range, that peak, and the existing highest peak. Okay. Now, the real key here is where do we stop? For where do we stop the Y search? Now, my just not smartest solution, I could say, I'll just let it run up to something high, like 1,000 or something, and surely we will figure out what we need to do there. And if I did this, I would probably get a right answer. I would not be very proud of myself, but we can kind of say what the hell. So I mean, let's just go ahead and see what it does with sample input. Okay, did we not? Oh yeah, that's what we did there. So we'll go ahead and print out highest peak down here. We should figure out a way to actually get the terminating position though, but I'm just going to say highest peak, and then let's give it a run. Okay, that gives us the correct answer for the sample input. I am not proud of this, but we will see what we do with this brute force search with our actual puzzle inputs now, and we will put that into the website and just see where we get to part 2, and maybe we'll get something more interesting. Okay, that's 1 gold star for part 1 at long last. The fancy trick shot isn't the best idea. After all, you only have 1 probe, so you better not miss. to get a better idea, you need to find every initial velocity that causes the probe to be eventually within target area after any step. Okay. I mean, this is actually like relatively simple. We can do the same stuff. It's just instead of like terminating early with found, so we'll just say valid velocities is 0. Here we will just increment valid velocities. We will not break there. We will not break there. We're not even doing anything with highest peak here. And then we can print out the total number of valid velocities. 5,569 for our actual test input. Let's see what it does. That is not correct. Your answer is too high, apparently. Okay. Let's try running it with the sample stuff instead of our actual values and see if it gives us a too high number for that as well. Gives us 119, and the actual is 112. So we are miscounting in some way. Gonna go ahead and get rid of all our actual trying to solve this with calculus. I apologize for doing calculus. I swear to never do it again. I don't actually mean that. I will, of course, do calculus again in my life. So why are we overcounting is the question. Are those ranges not inclusive? At least 20 and at most 30. Okay, so like these XY ranges should be inclusive. Well, let's print out what we think the valid velocities here are, I guess. So we'll just say candidate dx candidate dy. And then see if it looks similar to the list that we have on the website. Well, at least in its extreme ends, it looks correct. I wonder if that factor of 5 that we're off by is universal. So I'm going to take our previous bad value here and subtract 5 and just see what it gets us as just a random wild guess. Okay. Answer's still too high, so it's not off by a constant factor. Unfortunately, what it's showing us on the website here isn't like particularly well organized. The way that that we would have probably preferred, because well, I guess like our loops are Y major, and I don't really even understand like how this is sorted out. But obviously, we have more in our answers than the than we should. Oh no, it's 112, 119. So it's off by a factor of 7, not by a factor of 5. Do math better. Well, I'm gonna again. If we're off by 7, are we off by 7 all the time? We'll see. Okay. So still no. I mean, we got the correct peak before. Like we got things right on part 1, and our count is close in some way. But I'm very interested to see like what the overcounts are. So like 7, 9 is there. 6, 9 is there. 7, 8 is there. 6, 8 is there. Yeah. So basically, we get all the 11 numbers from 20 to 30 inclusive in X for anything that hits the target in one step. And then the range, starts to narrow here. So you got 8, -1 appears twice. So why are we going to certain X, candidate X's twice? Okay. Something interesting is happening here. So I'm seeing, yeah. If the same thing appears twice, why does it appear twice? So candidate DY, we are just, oh, sorry, I should have shown this here, but you can see like 8, -1 and 8, -1 appear twice in our debug output of, good candidates, essentially. So candidate Y, we are not messing with anything. These all take arguments by value, not by reference, so that's fine. Candidate X. Oh, because we go through steps. So if the same trajectory would land, would actually in more than one step be in the target range, then we're double counting it. So, easy enough solution to that. We will put them in a set. That is, yeah, because that should solve our double counting problem. Maybe not the most efficient way, but it works. And we will use some of our grid stuff too, because I'll make it a set of vex. So now with double counting eliminated, oh yeah, we actually have to put some stuff in our build file to declare those new dependencies. So grid2 for my little geometry library, and the abseil flat hash set library for the container that we use. It's grid2.h, not grid.h, sorry. Apologies, compiler. What? Oh, is this in place not working right? Okay. Because we don't actually have a two-argument constructor for vec. So we'll just say... Actually, I wonder if we can just put squiggly brackets there, and nope. Does not like that. Now we get the correct answer. We can remove that debugging statement, and we can do it for real with our actual puzzle input. $5,200. Now let's see if that is actually factually correct. Whew. Okay, that was a rough one, folks. Yeah, 4026 and 3656. Not great on the overall stats today. But, you know, we got to the problem eventually. So, you know, this is a bit ugly, and I will probably do quite a lot to clean it up, and maybe tomorrow night I will tell you about how I cleaned it up. But first and foremost, you know, definitely wasted some time trying to solve it with calculus, which is not the right way, because all the stuff I was trying to do with the quadratic formula, that works if you're under continuous acceleration, and although this problem like sounds like you're under continuous acceleration in the y direction from gravity, it's actually applied stepwise. So I did not have the right formula to work that out. Kind of a brute force search here, and the upper y bounding is not great. The x bounding is not great, but you know, like the search space is small enough that, you know, we could do an extra big search space that would be pretty much guaranteed to cover like whatever's in our input, and still get to where we would, you know, actually and still get the answers that we need ultimately. Is, you know, this, And then there was the double counting. That was like genuinely an algorithmically interesting thing where we double count things that actually at 2 steps are in the target area. So some significant mistakes, some significant ugliness, some significant slowdown tonight. Um, I maybe was not on my absolute best game, but hey, we got there. And sometimes that's what programming's like. Sometimes that's what using C++ is like. You try different brute force things, you go down different garden paths, you get to something ugly, but ultimately you get to a solution, and you take a step back, and knowing more about the problem, maybe you can come back later and make it prettier, make it more elegant, make it more robust. But sometimes it is just like getting that little more piece of the problem solved, even if it's in an ugly way. You're still making progress, and I hope that you feel that way too if you're watching, and that you don't get discouraged when your code isn't as nice or as beautiful as you think it should be, because it will be eventually. But sometimes you just need to make progress towards understanding the problem more and getting more towards the solution. So thank you all for watching. I hope you enjoyed the stream. I will be back here again tomorrow night solving the next day's puzzle drops. If you are watching this on the Twitch channel on the live stream, remember you can check the channel profile. There you'll find links to my YouTube channel with stream replays and to the GitHub repo where I upload all the code that we write in these sessions. If, on the other hand, you are watching on YouTube, on the replays there, just check the video description right down there. Once again, you're going to find links to the Twitch channel for the live streams and to the GitHub repo where all the code lives. Thanks again for watching. I hope to see you tomorrow night. Bye-bye.